Good morning and welcome back to our physics class. So yesterday in our class, we discussed alternating current, the theory part of alternating current, and when AC is applied to a resistor, what happens? When AC is applied to a inductor, what happens? When AC is applied to a capacitor, what happens? That things we discussed, and how the phase will change. And once more, if you discuss that one, where in the resistor there is no phase difference between voltage and current will be in phase. And in the case of an inductor, the voltage and current, if you take, the voltage will lead and the current will lag. And we have the inductive reactance there, omega XL. And in the case of capacitor, we have the current leading by an angle of pi by 2. And the reactance also we discussed. And in the case of inductor, it will allow DC to pass freely to that one. When the frequency increases, it will block. That is, it will higher frequency, it will block, lower frequency, it will allow to pass through that one. In the case of capacitor, it was opposite. The DC cannot pass, DC cannot pass through that one, and this AC can pass through that one. So all those things we discussed. And after that, we discussed about the LCR circuit. So in LCR circuit, what happens, the phase difference phi, all those things we discussed. Now we will do some questions based on this concept, even the transformer, the step down transformer, step up transformer. So this chapter in chapter AC, we will do some problems first, then we will go to the other topics. So one by one problems we will deal here. So these problems are the problems which is actually previously came for the examination, and there is a chance for now to repeat the questions, not the same with the same numbers, but the similar questions can come this year also. So we'll deal the questions one by one. Different types of questions are there in this one. And you can see the first question. I think it will be clear for reading this one. If the RMS current in a 50 hertz AC circuit is 5 ampere, the value of the current 1 by 300 second after the value becomes 0 is. So first point is we should understand the situation, what is happening here. So we have a AC here like this. So the AC is vibrating like this, okay. So we have AC which is going plus minus like this. So this maximum value, this is the V0. And here we are discussing about the current. So I will take it as I, okay, I0. So this will be I0 here. And it is oscillating like this. So the RMS current in 50 hertz. So the RMS value, which is coming somewhere here, that is 5 ampere. The value of the current 1 by 300 seconds after the value becomes 0. That is starting here, it is 0. And after a time, 1 by 300 seconds. So here we have a time where the time is 1 by 300 seconds after the value becomes 0. So what is the value you have to find out? So this is not from the graph actually. You have to write the value of current. We have I is equal to some equation is there. So we have to put that to these values in that equation. That is, you have to use the value of current and this time in that equation. And the frequency also given 50 hertz is there. So frequency is given 50 hertz means we actually in the equations we were using in two ways. Directly you can use the frequency, or you can convert this one into omega also. Okay, this is frequency f, or we can call it as f or nu. So this 2 pi f is the omega. So we can convert it and use, or we can directly use it. So you'll see how it is done. So this is a solution for that. So the explanation for that one. So we'll see how it is done. First, we will see what are the values given here. Once more, we will go to the situation. We have a AC circuit. In that AC circuit, the frequency is 50 hertz. And the current value, RMS value is 5 ampere. We have to find out what is the current after a time 1 by 300 seconds. So here you see the given value is IRMS is 5 ampere. 1 second, I'll use the mic so that the sound will be okay. So the IRMS is 5 ampere. Now we have N is equal to 50 hertz. This N or frequency this is. So time is 1 by 300 seconds. Now the thing is, our equation is in the form I is equal to I0 sine omega t. This is the format. So we need the I0 value because we got I value which is 5 ampere, but I0 we need. We don't want the RMS value when you are writing in equation. So this how you can get it? So the peak value will be, you know that this RMS value, IRMS means it is I0 divided by √2. So this I0 will be IRMS into √2. So we will use here the √2 IRMS is taken here. So √2 into 5 you have to take. So √2 means it will be 1.4 or almost 1.41. So you have to multiply that one, or you can keep it like that only. Okay, now how we can substitute in this situation? See here, I0 sine omega t is there. So it is √2, 5 into √2 sine omega t. So omega, I already told you, this omega is 2 pi nu. So this is omega into t. So you just substitute that one. 5, this is the I0 value, sine this 2 pi into this value. When you do it, you will get this one. 5 into √3 by 2, that value you will get. That value is already here. Actually, the thing is, if you take this 1.4, that will be difficult. Here already in the answer it is √2 like that is there. So better to use the √2 for is that. So the option B, which is here, this option is correct. Okay, so this can come as a question with the options MCQ, or it can come as a part of other program also. Just you can get this one as a numerical question, not as this one when it is coming as a theory part, a part of this one, part of the, for example, even for a 5-mark question, as a part you can get it. Okay, so this question's answer you can get like this. Okay, for this option B is the correct answer for this one. So what you have to take care here is the frequency which is given here is in hertz. When it is given in hertz, you have 50 hertz means it is the normal frequency. It is not the angular frequency omega. If you want to take angular frequency omega, it will be actually not hertz. Actually, it will be radians per second, like that will be there. Otherwise, they will mention it as omega. So this 50 hertz, when it is coming, you should be careful about that value. So this is how you have to deal the question. So more than the numbers, how to do it, that's important. Okay, so the same simple equation only we have I is equal to I0 sine omega t. This one only we have to use. But the thing is, omega is not given. You have to find out omega. I0 is not given. You have to find out I0. Then you have to do that. So now we'll move to the next one. Okay, go to the next question. So this is almost a direct, simple question. So we have to expect such questions also. When the frequency of an applied alternating voltage is very high, then what will happen? So see here, a capacitor will tend to become short, an inductor will tend to become short, both A and B. No one will become short. So what is the meaning of becoming short there? Short means it will allow the current to pass. So you have a very high frequency. So we remember that equation, this XC and XL. So if you take the value of XC and XL, you can see that when high frequency comes, if you have an inductor, this inductor will oppose high voltage. But in the case of capacitor will block DC and it will allow AC to pass. So here you can see for high frequency, which will become short, this capacitor will allow to pass. So the capacitor will become short. Short means it will make the current to pass through that one. It will not have any effect. But inductor is not like that. When you connect inductor, it will oppose. But if it is in the case of DC, it will be difficult. Okay, it cannot pass through that one. So what you should know is in any circuit, you see here, if you get any circuit again in a AC circuit, or if you have a DC, that is different. If you have an inductor here like this, and any solutions is required, you should know when it is DC, that DC will pass through this one. If it is AC, it will not pass. So it can come in a combination of circuit. So there, actually, when you study diode also, you will understand somewhere in the circuit such a component is there, means you should know whether the current will pass through this one or it will block. Okay, just like if you take the 10th standard questions, if you have ammeter and voltmeter, you can see that if ammeter is there, the current will pass through that ammeter. If voltmeter is there, means it will not pass. It is just measuring the potential difference. Same way, whether it will allow to pass or it will not allow, that depends on whether it is AC or DC. So you should be very much careful when a circuit is given. You are solving there, in that one capacitor and inductor is there. So whether it will allow or it will block. If it is a question based on AC, it may not be like that. A question in DC, where this capacitor or inductor is used. So whether it will allow to pass or it will block, that you should be careful about that one. Okay. So now we will move to the next. Now its explanation is given here. You can see that one. This XC is equal to 1 by omega C. That is they written as 1 by 2 pi C. That is same thing only. So as frequency increases, this XC becomes smaller and smaller for every. So this is about the capacitor. So the, see here, the graph is like this. When the frequency increases, XC becomes smaller. This XC is reducing. So this is opposition actually. So at higher frequency, the opposition is less. So it will allow it to pass. So that is the important thing. That is when the frequency increases, the opposition reduces. So the capacitor will allow this to pass through that. Okay, for AC, the capacitor will allow. So XC will be too small, which may consider as short. I'll move to this one. See here, the power factor in series LCR circuit at resonance. So we yesterday discussed what is power factor. I think you remember that one. That is, we have cos phi. This cos phi is power factor. So cos phi is 1, means the maximum current will pass. Okay. So in the case of a resistive circuit, pure resistive circuit, cos phi will be equal to 1. So you should not confuse with this phi and the cos phi. Okay. Because power factor is not phi, this the total value. Cos phi is called power factor. So in the case of LCR circuit, the phi value will vary. But at the resonance, this cos phi will be 1. So the maximum power dissipation takes place in this when the cos phi is 1. So in resistive circuit, we have cos phi is equal to 1. And in resonance also, we have cos phi is equal to 1. So that the maximum power dissipation takes place. So this is another question. Now we have one more question here. See here, an alternating voltage is given by V is equal to this. This equation is given. An alternating voltage is given by V is equal to 140 sine 314t. Why this 314 comes, means it is actually 3.1 is actually pi. So it will be a multiple of pi. That's why it's easy. In most of the cases, it will be 3.1 something like that, or it's multiple. So that easy calculation will be easy. 140 sine 314t is connected across a pure resistor of 50 ohm. Find the frequency of the source and the RMS current. So this is connected to a pure resistance, means it is not going to change. So just for this source only, from this one only, we had to find out the value of current and the frequency of this one. So how you will get frequency? From here only you will get. See, actually our normal format is V is equal to V0 sine omega t. So in the place of omega, what is coming? This 314 is coming, and in the place of V0, we have 140. So from that one, we can calculate the frequency, and we can calculate the value of current also. So we'll see how to do it. So here, this omega is 2 pi nu, that is 314. So if you calculate that one, you can 2 pi nu is equal to 314. So now if you take this nu is equal to 314 divided by 2 pi. If you put the value of pi, you can get it as 50 hertz. Okay, so this one most of the people remembers actually, because our normal electrical supply in home is 50 hertz. So that is 314 radians per second only. Okay, 50 hertz means 50 cycles per seconds. So that is our normal Indian power supply is 50 hertz, or it is 314 radians per second. Okay, so this is a commonly used number. Okay, so from using 2 pi nu is equal to 314, you can find the frequency. It's a direct question actually. Now IRMS we have to find out. IRMS is VRMS by R, that is voltage by R. So we have to find out what is RMS value. So this is very important. We are supposed to find IRMS. IRMS is VRMS divided by R. But in the previous section, when the equation is written, the what value is given is not RMS value. See here we have this one. This is not RMS value. This is V0. So from there you have to find out the RMS value. So how to get it? This RMS value means you have to 140 divided by root 2 you have to take. Okay, so you'll get the value there. So you'll get this much as VRMS. Then again you have to divide it with R. That's why here they taken 140 divided by root 2. This 140 by root 2 makes it to RMS value. And this is the resistance. We have to divide it with the resistance also. No, VRMS by R is there. So this 50 is the resistance. So you'll get this much 1.98 ampere. It's almost equal to 2 ampere. No, if writing like that, if you write like this also no problem. Okay, 1.98 you can write, or 2 ampere you can write. Okay, always when we are doing physics numerical problems, that small number difference will not make any problem. Only it will make problem in the nuclear physics chapter. That is coming on the second part. You might have not started that one in nuclear physics only, because you know we have the equation E is equal to mc square. So this c square is a very big thing. Okay, that is speed of light in square comes. So when you use this equation, if there is a small mass also, it will create very huge energy. So that's why when you do this equation and in nuclear physics, there only the small numbers will come as so much important. Here in other area, just from 9th standard onwards, you are doing, that is the value of G. When you are taking 9.8, you are taking, you can take it as 10 and do. So that won't make any big difference. But here it is not like that. In this case, you have to take very accurate value. So that's why if you 1.98, if you write as 2 also, it doesn't make any problem, or you can write it as 1.98. Okay. So that's another type of problem which we can come, or which will come from the AC topic. This is also a question based from AC. You see here, the figure shows a series LCR circuit connected to a variable frequency 200 volt source with L is equal. So what are the things given here? You see, the figure shows a series LCR circuit. So we have L here, C here, R here. Is a series circuit here. So this voltage source is, this is 200 volt. This is 200 volt here. Source with L is equal to 50 mH. So this is having 50 mH as its inductance. And capacitance is C is equal to 80 microfarad. So you should be very much careful. This is milli and this is micro. And R is 40 ohm. 40 ohms. Okay. Now, determine, you have to find out the source frequency which drives the circuit in resonance. That is, you have to find the resonance frequency. The equation you have to do. And you see here, the second part of the question, the quality factor. So this year, this is not there in the syllabus. So that's why we will leave it. Okay, quality factor, this year it's not there. So you forget about that. We will go for the first part. Quality factor, just yesterday I told you that is the resonance graph. The graph goes like this. So the sharpness of this one. So how much the resonance is sharp, that is determined by the quality factor. Now, as it is not there in the syllabus, we will leave it. So the source frequency which drives the circuit in resonance. So resonance frequency you have to find out. Okay. So that is direct substitution you can get. See here, the resonance frequency omega naught is given by 1 by root LC. But the important thing is when you are taking this value of L and C, it is microfarad and the millihenry. That is very important. So L value is 50 millihenry. That is 50 into 10 to the power minus 3. That is very important. And capacitor is 80 into 10 to the power minus 6 farad, because it was microfarad. Okay. So capacitor, it can come as an microfarad, it will come nano or pico, everything it will come. So according to that one, you have to put it as 10 to the power minus 6 or 10 to the power minus 9 or 10 to the power minus 12, like that. You should know which one, which suffix is used for how much is the value, like that. Okay, because only in capacitor this pico, nano and all will come. Here it will mostly it will come micro only. And the resistance is R is equal to 40 ohm. So the resistance don't have any role here in the first part. Okay, this is the quality factor thing which is not required for us. So here 1 by root LC, see 1 by root of this value, and you will get the value as omega 0 as 500 radians. So from 500 radians, again you can, the frequency is asked. So 2 pi nu is equal to 500. From nu you can find out from this one. So you'll get as 80 hertz. 2 pi nu is 500. So nu you will get it as 80 hertz from this one. So this is the way you have to find out the resonance frequency here. I think this will be clear. This is just substitution only, but still why I took this question means in the substitution also, these powers when you are doing and when you are taking the root of that one and all, it should not make any issues. Next, another question. This one also you see here. A circuit containing an 80 millihenry inductor. Here also millihenry is coming, and a 250 millifarad capacitor in series connected to a 240 volt 100 radians per second. So this is given in radians per second. So radians per second means it will be omega. You should be very much careful. If it is given as hertz, it will be nu, and when it is given in radians per second, it will be omega. The resistance of the circuit is negligible. So R is negligibly small. Obtain the RMS value of current. Here also substitution only is there, but this analyzing is important. This is milli, and here this 240 volt. This is not maximum, it is just 240 volts. So it will be RMS value. And here we have 100 radians per second. So it will be omega value. Obtain the value of current. So the question is to find the value of current and what is the total average power consumed in the circuit. So that also you'll see. Okay. Okay, so this is the, for this question, this is the calculation here. See here, actually, when you take the reactance or impedance, you remember that value, the impedance, how it was? Impedance, when you take it, was root of R square plus XC minus XL, or that difference was there. Okay. XC minus XL, that one was there. Now here you see here that resistance is not there, so we can neglect that one. So the value reactance will be omega L minus 1 by omega C. Just you have to put the values. So omega is 100 already given. Then this is 80 milli here, and this value also you have to put. Then when you do the calculation by substituting the value, we have this one. Okay, you should remember that resistance is not there. That's why resistance is negligible. It is given. That's why only these two we are using. Okay. Now the RMS value of current is RMS value of voltage divided by the reactance or impedance, whatever coming. So 240 divided by this one you have to do. Okay. So you see whether it is given 240. It is important there. Why this 240 is used? Because here it is given how much? 240 only. Okay. Okay. So we calculated I also as RMS value only. That is 240. If peak value means this 240, you have to multiply with the root 2. Okay. The question is for RMS value, and our value given also RMS. That's why directly it is done. Okay. Then the question is the average power consumed by the circuit. That is, average power consumed will be 0 because we have inductor, capacitor both. Okay. So the average power consumed will be 0. There is no resistance. We already discussed that one. If you have in an LCR circuit also, the power consumption takes place across the resistance only. So if the resistance is negligible, then there will not be any power consumption. Another question here. In a series LCR circuit, the voltage across the inductor and the capacitor and the resistor are 30 volt, again 30 volt here and 60 volt here. You see here, this is actually a little bit important thing. In an LCR circuit, the voltage across an inductor, capacitor, so voltage across inductor is 30 volt, and voltage across capacitor is also 30 volt, and voltage across resistor is also 60 volt. That is 60 volt. So here always one confusion comes. So before going to the detail of this question, let me tell in general. You have an inductor here, and you have a capacitor, and we have a resistor also. And this is connected to a particular source. For example, AC source, it is connected here. Now, what happens is, here we have 100 volt. Listen carefully. Here we have 100 volt. When you use the normal techniques which you are studying in 10th standard, if here it is 60 volt, here it is 30 volt, here it is 30 volt, then the total voltage, okay, this 100 you don't take it. So 60 plus this one is 30, so it will become 120. But in AC circuit, it is not like that. Okay, that you have to remember. That is, if you add, even this one is in series, if you add the voltage across this one and voltage across this one and voltage across this one, if you add all the three voltage, you will not get the source voltage. In DC circuit, if you have three resistors, if you add all the three voltage across three resistors, you will get this one. In the case of AC, you will not get it. So there is a reason for that one, because this value, this is the RMS value or peak value we are taking here. This voltage is not coming at the same time. You understood? That is, when this is 60, this is always 60. It's okay. But this is a varying voltage. So this varying voltage means it is just like a wave. This is also like a wave, but not with the same phase. So when this is 30, this may not be 30. This can be 0. When this reduces, this may increase because there is a phase difference. So this total voltage, if you add, you will not get the source voltage in the case of LCR circuit. That is very important. So now this problem also based on such a concept only. So this 30 and this 30 is there. So you cannot add this 30 and 30 because this 30 goes maximum and the other 30 goes maximum. It's not at the same time. There is a phase difference. It is at different time. Okay, so you will see the answer, then you will understand. See here, the phase difference between the applied voltage and the current in the circuit will be 0 because VL is equal to VC. That's what it is given here. VL and VC are same. So the phase difference will be 0. That is, the effect of the capacitor will be cancelled by effect of the inductor. So you have a capacitor here and we have a inductor here and we have a resistor here. Now what happens is, you see here the phase difference of applied voltage, the voltage and current in the circuit will be 0. That is, this is 30 voltage, this is 30 voltage. So when these both are 30, the effect of this one will be cancelled by that one. The phase difference will be cancelled by that one. So it will be just like the resistance. That's all. Okay. And in the case of voltage also, you should remember, if you add these two, all the three, you will not get this voltage here. Okay, this should be AC. You will not get that one. Okay, if again such problem is there, it will be clear. You will see whether again such questions are available. This is about the transformer. Yesterday we discussed the last moment. We couldn't make it that much clear. Still, a step-down transformer operates on a 2.5 kV line. It supplies a load with 20 ampere. The ratio of primary winding to the secondary wiring is 10:1. If the transformer is 90% efficient, calculate the power output, the voltage and the current in the secondary. So I will deal this one before going to the answers. You have a transformer here. The situation you have to analyze. You have a transformer here. So we have a primary and we have a secondary also. And already it is told it's a step-down transformer. So when it is a step-down transformer, the primary will have more turns. That is, the number of turns in primary will be more than number of turns in secondary. Similarly, voltage also. Voltage in primary will be more than voltage in secondary. So already here given the ratio of turns. So here when turn is there, this will be in the ratio 10:1. For example, here 100 turn is there, means here 1000 turn will be there. So that it reduces the voltage. That's why it's called as a step-down transformer. And the step-down transformer operates in a 2.5 kilovolt lane. So here it is 2.5 kV. Very high voltage is there. That is 2500 volt. Very high voltage is there here. So it reduces here. So you see here, what we studied previously is the ratio of this NS by NP, or opposite also you can, will be VS by VP. Like that we can reduce the voltage. But you see here, the voltage we can reduce, current also we can take in the same ratio opposite, like that we done yesterday. That is IP by IS. But you remember this current and voltage derivation, from where we done this one? We taken VS into IS is equal to VP into IP. That is, we taken the concept that the primary side and the secondary side, the power is same for an ideal transformer. But here this situation is different. This is 90% efficiency. So the efficiency is 90% means what happens? The primary and secondary is not having the same power. So we cannot take it like that. Okay. The secondary will be 90% of the primary only. So 10% this energy is getting wasted. So how to deal that situation, we will see. So here you see, given that the primary voltage is this much and this converted here, and the primary current is 20 ampere, whether it's given 20 ampere is given. Supplies a load 20 ampere, that's given. Okay, so it's given there. Okay, the current in the primary also is given. The input power P input is, it will be voltage into current. So the power input is 50 kilowatt. So see here, the power in input is the voltage in input, V voltage in primary into current in primary, that is equal to 50 kilowatt. So no issue in that. But next the problem comes. The efficiency was 90% only. So when the efficiency is 90%, what is the meaning? The eta here is taken as efficiency. P out by P in. This was 90%. Okay. So what you have to do? Our power is 50 kilowatt here, which is in the input. Okay. But in the output, you will not get the same power. You will get its 90% only. So 90% of 50 kilowatt is this 45 kilowatt. Okay, so we are getting 45 kilowatt. That is 0.9 into this one. If you do, you will get 45 kilowatt only. So a little bit energy loss is there. Okay. Now see here, voltage across the secondary. So here you see voltage across secondary, we taken Vs by N. See here, voltage just in the same ratio only we taken. Vs into Vs by Ns is equal to Vp by that calculation you done directly, you substitute the value and you got 250 volt only. But you see here, current, what happened? Is is equal to P out by Vs, that is 45 into 10 to the power this 3 by this. So what I want to say you is what we changed here actually, the ratio. This is actually supposed to be, if 100% efficiency means it should be actually 200 ampere. So you see here, when the efficiency is less, efficiency is 90%, the voltage ratio is taken same, and the change happens for the current. So current is not this one divided by 100. It is not done like that. Okay. So the ratio that current reduces actually. So here you see, this one is 45 only is taken. That is, we taken in such a way that P out by Vs, or P out is this 45. Okay. Or you can directly take the ratio of the current and multiply with 0.9. Then also you will get the same thing. So you should know that the current reduces there. When there is a problem in efficiency, the voltage ratio remains same and the current reduces in that case. Okay. So this type of question also can come. This simple type of question can come because of your competency based question, because one transformer diagram and some details about the transformer is given. They can ask so many questions about that one. About what is step down, what is step up. They can ask this numerical. So you should be careful about such topics where you can give a feature and some details, and so many questions can be asked. So such a area, from such area only you will get more this competency based questions. Okay, you have competency based questions based on such. So transformer is a area where you can get such question. Just in LCR circuit also you can ask so many things about that one. So LCR circuit, transformer and all, you can get competency based questions. Okay, actually competency based questions I cannot keep it on the board and explain to you, because it actually competency based question that actually measures by seeing this one and reading that question, how much you are able to comprehend that one. If I give the questions here and I will explain the entire thing, means you will get the answer. But the task is not that one. By seeing that diagram, you yourself should do it. So that's why it is difficult for to explain and make you do that competency, because it actually checks the competency. So for that one, you should know the content. So now we'll go for another question. So an ideal inductor of 5 by pi Henry inductance is connected to a 200 volt 50 hertz supply. So calculate the RMS and peak value of the current in the inductor. This is just substitution type only, but it is taken because it is came CBSE examination. Okay, in foreign 2020, the foreign set it was there. So it's a CBSE question. That's why it's again taken. It is something similar to what we did. See here, calculate the RMS and peak value of the current in the inductor. So the values are given, you have to do. What is the phase difference between the current through the inductor and the applied voltage? How will it change if a small resistance is connected in series with the inductor in the circuit? Okay, so see here. See here, here the given value is L is equal to 5 by pi Henry, and this V RMS, it is given as E here, that's V only, 200 volt, and the frequency nu or F, that is 50 hertz. Now this XL, inductive reactance XL is equal to 2 pi nu or omega naught into L. That's given here. So you will get this XL as 500. Okay. It is not Henry. Okay. Now see here, the RMS value is ERMS by XL. So you divide with that one. See here, this is voltage by resistance, it will come. So you will get the current as 0.4, direct substitution only. And if you want to get the peak value, you have to multiply this one, whatever we are getting here, into root 2, 1.414 you are multiplying. So you are getting the peak value of this one. And the second part you see here, the current through the inductor lags behind the applied voltage by pi by 2. So here you can see there is a inductor is there. So inductor voltage leads. So current will be naturally lagging. So it is lagging behind by an angle of pi by 2. That's given here. Okay. So this is just substitution only, but you should do it in the correct way. Okay, that's all. Now we have another question. A capacitor of 1 microfarad is connected to an AC source of EMF E is equal to 250 sin 100 pi t. Write an equation for instantaneous current through the circuit and give the reading of AC ammeter connected to the circuit. So here a capacitor of 1 microfarad is connected to an AC source. It's given here. A capacitor of 1 microfarad is connected to an AC source of EMF E is equal to that. So this is our V. V is equal to 250 sin pi 100 pi t. So this omega is 100 pi here. Okay, omega is 100 pi here. So 100 pi t like that. Write the equation for instantaneous current through the circuit and give the reading of AC ammeter. That is, you have to take the current through that one. So we'll see like this. See here, the capacitance is given by 1 microfarad. 1 microfarad means 10 to the power minus 6 farad. And the V0 or E0 is given by 250 volt. And the omega value is given as 100 pi radians here. The instantaneous current through the circuit. So just we are writing the equation for that one. I is equal to I0 sin omega t plus pi by 2. So you see here from voltage, when you are taking current, there will be a plus pi by 2 will be there in the case of current. That is in capacitor current leads. So this plus pi by 2 comes here. Now you see here, what is I0? I0 is equal to, already we got the voltage. See here, in voltage, you have to multiply with omega C. Okay, that when you multiply with omega C, you will get the, this is the previous value. We are multiplying with omega C, so you will get the maximum value of current. The remaining part is same only. I think it's clear for you because this I0 is here. The maximum value of current I0 will be this one. That is the maximum value of voltage into XC. So XC will be this omega C. Okay, not into XC, it is by XC will be there. The XC is 1 by omega C, so it will come to the top like this. So when you substitute all the values, you will get this equation like this. So this area, when you do, you will get it as 0.076 sign like this. So this is the equation. But the important thing is the second part is asking what is the value or the reading of an AC ammeter here. So when you connect an AC ammeter, the value which the AC ammeter giving is not this value. This is the peak value. The AC ammeter will give you the RMS value. So from here you have to convert it into RMS value. So this like this you are getting it, and we have to convert this one into RMS value. How to take it? Take its RMS value. So this one you have to take 0.0786 divided by root 2. Okay, divided by root 2 means it is same as multiply. So that is divided by root 2 is same as multiplying with 1 by root 2. So this 1 by root 2 is actually 0.707 or at least 0.7 you take. So that you remember for easy calculation. That is whenever you have to multiply with root 2, you do it with 1.4, and when you have to divide it with 1 by root 2, or when the root 2 comes in the denominator, you take it as 0.7. So it will be easy for your calculation. Okay, so you will get this value of the current. So this is the RMS value. It's very important. The reading which is seen in the ammeter is RMS value, not the peak value. Always it is based on peak value. And one more thing is there. This ammeter, AC ammeter and the DC ammeter, the working is different. Okay, so you might have seen in your lab you have the DC voltmeter and DC ammeter and all, and the AC is not working based on this mechanism. You studied the galvanometer, how it works, galvanometer, moving coil galvanometer. So the needle goes to one side and all. But you know, in the case of AC, it is not like that. AC, what happens? It will go both sides. So 50 times it will go both sides. It will not show a. So this moving coil galvanometer, that principle will not work for this this one actually. So for AC, we are using actually the heating effect of electricity or some other method in digital, some other method we are using. Not the principle of the moving coil galvanometer for AC ammeter and voltage. So that's why you might have noticed that one. Mostly the scale is not linear in the case of AC voltmeters. Okay, because there are some square term and all is coming. So just if any, in case any question comes about that one, you should know that one. Because moving coil galvanometer we are using, that we can convert into ammeter, we can convert into voltmeter and all. So that is applicable in DC only. So AC, the ammeter, voltmeter and all, the principle is different. Okay, so how we are using that is the principle is different. So that's why even in the AC that is not linear. So previously question used to come like that. Why this AC ammeter, it is the scale is not linear and so you should know that it is not working just the principle of moving coil galvanometer. It is making the heating effect of this one or any other effect, not this direct conversion using the magnetic field, because it will also at both sides. Okay, so we'll come to our topic. We have one more question here now. So this is when an inductor L and a resistor R is in series are connected across 12 volt 50 hertz supply, the current is 0.5 ampere. So you see here it's not that clear, I think. So I will tell that one. The inductor is having L here and a resistor R, and here you see here the frequency is 50 hertz. 50 hertz already we told you have to convert it into omega, so 314 it will come. A current of 0.5 ampere is passing through that one. The phase difference applied voltage, it is given by pi by 3 radian. Calculate the value of R. You have to calculate the value of R. We will see how to do it. See here, here the RMS value is given as 12 volt. Frequency is given as 50 hertz and IRMS is given this one. Okay, so the impedance is given by, or the opposition is given by ERMS by IRMS. So you will get 25 ohm. See here, this impedance, reactance and all, it should be in ohm only. The previous one it was given as H. That's wrong. Okay, because this impedance and reactance and all, how it is coming? Voltage by that quantity gives the current. So voltage by something is current means this denominator should be resistance, or it will have the unit or dimension of resistance only. Okay, so you got this one, impedance is equal to 24 ohm and cos phi is equal to R by Z. So this one, from where you are getting cos phi is equal to R by Z, we had that impedance diagram. Remember yesterday we done that one. Here phi was there. So in that one, you will get cos phi is equal to R by Z. So R is equal to Z cos phi. You substitute the value, you will get it. I think it's clear, because the relation between R and Z or XC, XL, all those things we are getting from that impedance diagram. So you should study that one. So from that one, you will get cos phi is equal to R by Z. Here, this side Z was there, this side R was there, this side the difference between XC and XL was there. So the cos phi will be this R by Z. Okay, so from there you will get this one. So many questions will come based on that one, where we have to relate this one. So this diagram, it should be clear. Okay, so cos phi is equal to R by Z. So R is equal to Z into cos phi. If you do this one, you will get the value of resistance also. This is how you have to do it. So in all these things, just mostly direct substitution. But when you are doing the substitution, this RMS value and the peak value, that conversion will be there, and the frequency conversion and this micro milli, that conversion, all those conversions you have to do. Now, another question here. A bulb of resistance 10 ohm. When you use a thing, a bulb, it is can be a resistance, okay, because in that one a filament is there. A bulb of resistance 100 ohm connected to an inductor of inductance L in the series with an AC source marked as 100 volt 50 hertz. If the phase angle between the voltage and the current is pi by 2 radian, calculate the value of L. See here, a bulb of resistance, the resistance of the bulb is given here, connected to an inductor of inductance L. So inductance value is not given. In series, so we have a resistance and an inductor which is connected in series with a source. Okay, AC source, with an AC source, and this source is 100 volt 50 hertz. If the phase angle between the voltage and the current is pi, that is phi is pi by 4, calculate the value of L. Okay, before going to the problem, let me tell you one thing. Here one thing is that bulb is given. So one reasoning thing I will tell you. If you see the AC bulb which we are using, the normal bulbs which we are using in your home, I am talking about the normal tungsten filament bulb. Have you seen the filament like this? So here, if you notice that filament very much carefully, you can see that it is like a coil like this. Inside that one, it will be. So if you take a DC bulb or normal bulb which is there, that coil shape will not be there. It will be a straight line. And in the case of AC bulb, there will be a coil. So why it is like that? Because this one also gives some opposition. Because if you have a resistance wire, it can be taken as a normal resistance wire. But when you make it into a coil, it becomes inductor also. So it will add some inductance also to that. So that's why this this filament is like a coil. And you can see the most of the heating elements, everything will be in the shape of a coil also. Okay. So now we'll go for the solution of this one. So you see here R is equal to 10 ohm, it's already given. And frequency is equal to 50 hertz, that's also given. And the phi is equal to pi by 4, all these things we just now we written. Now the tan phi is equal to XL by R. So this one also, from where you are getting same that diagram. Here phi is there, here R is there. So if you take from there, you will get actually XC, XL, that difference comes. C capacitor is not mentioned here. So tan phi will be equal to XL by R. Then what is XL? XL is equal to omega L will be there. So omega is 2 pi nu or 2 pi f. Put the value of R. Just solve. So you'll get the value of L and it is in Henry. Direct substitution only, but the step by step you should know, and you have to take this tan phi from that triangle. You have to take tan phi. Tan phi is equal to this one. You rearrange that one, so you'll get that one. Okay, tan pi by 4 you have to put, and you have to do it. Okay, so you'll get the answer using this one. Now, next question. So all these questions are almost similar only, but it is again and again given because it is different years question. Okay. When an inductor is connected to a 200 volt DC voltage, a current of 1 ampere flows through it. When the same inductor is connected to 200 volt 50 hertz AC source, only 0.5 ampere current flows. Explain why. Once more, when an inductor is connected to a 200 volts, that is 200 volt DC first you are connecting. You have an inductor and it is connected to a DC of 200. 200 volt DC, when it is connected, a current is flowing which is 1 ampere. And when the same thing is connected to a 200 volt AC, the current is 0.5 ampere. Explain why. Very simple, because here it is having a resistance. The inductor is a coil, it is having a resistance. Due to that resistance only, it is 1 ampere current is passing through that. Here when you connect to this circuit, you know, two effects are there. That is, you have a resistance for the coil, that is one effect. And the other effect is this works as a inductor also in the case of AC. That's why it reduces. Calculate the self-inductance of the coil. That is a mathematical step is here. So for DC circuit, it is given here. See here, for DC circuit, only resistance is taken. R is equal to V by I. So if you calculate the resistance, you will get 200 ohm is the resistance. Now you see here, in AC circuit also, if you calculate, instead of 200, it will become 400. Clear? So in AC circuit, it will become 400. So this 400 is this value. Okay, so from this one, if you calculate the value of L, you can calculate. Okay, so S Z is equal to root of R square plus XC, like that. If put the value of that one, and XL, you can, this equation only, you are supposed to find this XL. You rearrange that one and you will get the value of L from that one. First, you can find XL. From XL, you can find the value of L here. So all these are substitution and rearranging only. But the steps you should know what to do like this. Okay, so you can just note down that one, how it is. First, you have to find the resistance of that one. Only resistance is there, no inductance in DC. Then in AC, we have 400. So the remaining 200 is due to the inductance. So we got that one as 200. So now Z is equal to R square, like this. This is the equation. So you, from this equation, you have to find XL. From XL, you have to find out the inductance value. You can find out from XL. Now one more question. In the circuit shown in the figure, the potential difference across the inductor L and the resistor R are 120 volt and 90 volt respectively. That is, in the inductor L and the resistor. So in across the inductor we have 120 volt here, and across the resistor we have 90 volt here. And the RMS value of current is 3 ampere. So the current passing is 3 ampere. Calculate the impedance of the circuit and the phase angle between the voltage and current. Okay, so this looks difficult when you see the values here, because here 90 volt is there, here 120 volt is there, this is 3 ampere is there, and you are supposed to find the impedance of the circuit and the phase angle between the voltage and current. You see here, you cannot directly add this one. Okay, but here only one is there, so it will not make any issue. And if you have capacitor also, that makes a problem. So we have 90 volt here and 120 volt here, and you have to find out the impedance of the circuit and the phase angle between voltage and current. We'll see how to do it. So first itself, the voltage across L and R are 90 degree out of phase. That is, the resistance and the inductor is given. There is no capacitor. So resistance, the voltage and current will be in phase. And in the case of inductor, it will be out of phase by pi by 2. So there is a difference between these two voltages. So that will be 90 degree out of phase. Their resultant voltage is, so this is important. See here. So we got one is 90 volt. See, this is 90 volt and this is 120 volt. So the total voltage, we are not directly adding this one. There is a angle difference between this one. This 90 volt and this 120 volt are in different angles. See here, yesterday for LCR circuit we done. So this R, it is like this, and L, it is like this. Now how to get the resultant voltage? This is VR and this is VL. So we cannot add this one directly because there is an angle. So this one we have to take here, and this resultant you have to take. So this resultant will be root of this square plus this square. That way you have to do. So you see in the next one how it is done. See here, that same thing. So the VRMS will be VR square. So this, like this you have to do. So you put the values and you will get 150 volt. So once more you come back. Now you see here, that's what I told. Here 120 volt is there, here 90 volt is there. So this 90 volt and 120 volt, if you add, you will get how much? It is getting 210. But that is not the voltage actually. See here, the value is actually coming 150 only. That is important here. Okay, so because it is in different angles. So when you are doing that one, you will get 150 volts. So just like DC, we cannot take it because there is a angle dependence here. So VR square and VL square, when you do, you will get it as 150 volt. And the RMS value of current is 3 ampere, which is given in the question. Now we have to calculate the impedance. Impedance will be the voltage by current. Both are RMS. So if you do, you will get the impedance as 50 ohm. The impedance is 50 ohm. See, this impedance is the combined effect of both, that the resistance and the inductance. So now again from the same, tan phi is equal to this one from that triangle, impedance triangle. So everywhere we are using that one only. So that point is very important. So tan phi is equal to XL by R. So VL by VR by XL by R is VL by R, because current, it is a series circuit. Current is same in both. So XL by I we can take, and this R also by I we can take. So XL by I will be VL and R by I will be VR. That is, XL is the opposition by our inductor. So if you divide with the current means you, you have to multiply with the current means you will get the voltage, not division, multiplying. And here also you are multiplying with the opposition, then you will get this one. So this value already we have. That's why we are using like that. So 120 by 90. So you will get 4 by 3. So phase angle is theta is equal to tan inverse of 4 by 3. So this is a problem here. This tan inverse of this one, how to find this tan inverse? Okay, so this tan value and all, if you got the log, this log table, in that one you have the tan values. From there you can do it. Or if you have any difficulty, you can stop here itself. Tan inverse of 4 by 3. If you write that much also, it's okay. Phi is equal to tan inverse 4 by 3. You can stop there. Or if you got the log tables, in that one values will be there. There you can calculate. Okay, because you cannot remember this one because what value comes we don't know. So these numericals are over now. So now we will go to another topic. Okay, so almost EMI and AC, the theory part also we done, and what are the possible questions which can come from that one, that also we done. And again I want to stress you on the competitive this competency based questions. So competency based question, if you whatever we done, if you are an expert with this one, this competency based question, you can do it. because I cannot do it because every time it's a different question. So the concept should be very clear. Okay, if it is required 1 or 2, we can do it just for example. But the thing is, it will be always a new question. Okay, so now we will move to the new portion, which is the electromagnetic waves. Okay, we'll start electromagnetic waves. So this is a topic where you can score more marks. Okay, so electromagnetic waves. Actually, if you take seriously, you will get 4 to 5 marks from this one, according to the this one. Actually, this is coming now. It's as a part of the optics actually. So 3 marks minimum you will get from that one, and sometimes it can be 4 marks questions also, or more can come from that one. So this is a very simple thing only. There is not much in that one. So mostly the waves, its characteristics, or its this one, what is that use, that is asked. Only that displacement current is there, something like a derivation. Remaining all are its use only. So first you will do the displacement current. You should understand what is the displacement current, then different waves and some properties of this one. So you should not think that we have some waves. For that waves, we have to study 2-3 examples or 2-3 users. That is not sufficient, because the question comes in the opposite way. Because they will ask you which wave is used for a particular purpose. For example, to study the structure of a crystal, which wave is used. So you study 2-3 examples. In that example, if it is not coming, then you cannot leave it. So all the properties and all the uses you should study. You cannot neglect anything, because they will not tell you to write 2 use or 3 use. They will give the use and tell you which wave is used and what are the other uses and such things. So you should identify the wave. So all the possible uses you have to study. Okay, so I'll start from the displacement current concept. Okay, this is also for most of the children, it's a confusing thing. What is this displacement current, or even the derivation of this one also? Okay, so I will do this one. Just this much only is there, but you should listen carefully. So here, what we are doing is, first we are analyzing this Ampere circuital law. See here, we are thinking about a capacitor. So we have a capacitor like this, the same picture. It may not be visible. That's why once more I am drawing. So we have a capacitor like this. So this capacitor we are charging. When you are charging this capacitor, a current I is passing through that one. So this side becomes positive and this side becomes negative. So this we are charging this capacitor. So a current is passing through this one like this. Okay. So now our problem is, you want to calculate the magnetic field at this point P. So if you want to calculate this magnetic field at that particular point, just if you want to find the electric field, we will use the Gauss law. If you want to find the magnetic field, we will use the Ampere's law. So for that one, we have to take a Ampere's, you know, the Amperian loop. Amperian loop means first you have to consider a surface and the boundary of the surface, that is called as the Amperian loop. So I am considering a surface here, just in the shape of a disk. I am considering a surface here. This requires a 3-dimensional view. That is, you have a wire like this and your surface is like this. This is passing through this one like this. Okay. So this is your surface and the wire is passing like this. And here we have a point at a distance R from here, and at this point only we have to find the magnetic field. Okay, so what we have to do? So from Ampere's law, we have this closed integral B dot dl is equal to mu naught I. This is our equation. Now, see here, this is the magnetic field around this wire will be tangential to that one. This dot doesn't have any meaning. Just you have to take B into that circumference of that one. Okay. You might have studied like that also. B into L is equal to mu naught I. Like this also we can write, because this is mostly it will be tangential to that one. So this B is the magnetic field, and L is means L is the circumference of that circle. You have a disc like this. See here, actually, this Ampere circuital law you already know. That's why I'm not going deep into that one. This whatever is there, this dl or the integral dl means that we consider a disc-like structure. Its edge or its boundary, that is important here. So that boundary will have, if it is radius is r, that boundary will have a length of 2 pi r. This is equal to mu naught into I. Now here if you take what is B from here? So B will be equal to mu naught I divided by 2 pi r. Okay, something you will get here. So just our point is we have a magnetic field at this point. That's all. That is, we will get a value for magnetic field in this point P. So the concept is you have a capacitor, and this capacitor, outside the capacitor we are taking a point, and a current is passing towards the capacitor. So you will use the Ampere circuital law and you will get a magnetic field here. Now the thing is, if you take a Ampere circuital law or any other law, the law should be valid in all the situations. Okay, so here you see, in that law is not telling in which way you have to take the surface. I can take another type of surface also. So now what I am doing is the same thing. I am taking another surface. Okay, this corner I will draw it. Okay, otherwise here only will do. So the same situation, we have a capacitor here. Here we have positive charge, and here we have negative charge. I mean, our point is here only. Okay, the point P is here only. In the previous case, we taken a circular disc type surface. Now we are changing it. Instead of this disc, we are taking like a pot. That is like this, an open pot, and this one line is inside that one. So the shape is like this. I am taking a surface like this, and this side is an open hole. Okay, this is empty hole, and this is inside that. So actually where this wire is going, there is, previously we had a surface like this. Now surface is not there, it's like this. And you have a this plate, capacitor plate here, it's like that. So our wire is not cutting any surface. That's important. Okay, so from the picture it is not clear. That's why I'm explaining. We have a pot. So this is our pot. Okay, this thing is our pot, and this plate is inside that one. And here we are not cutting it. Now we will apply the same equation here. What is the equation? B into L, or B, same thing, is equal to mu naught I. So we have the equation here. We have to apply this one. So what is this I here? I is the current which is crossing the surface. So here in the first case, the current I was crossing here. In this case is here. When it is going like this, the pot-like structure is like this. It is not crossing. It is just going inside, but it is not cutting that one. So what happens? Here the current which is crossing that surface, that is 0. So what happens? This becomes 0, means this total magnetic field becomes 0. That creates a problem. That is, we are using this Ampere's law. When you use Ampere's law, and if you take a surface like a disc, you are getting a magnetic field, a particular value for the magnetic field. And for the same thing, situation is same, point is same, and the Ampere's law, that's also same. Every procedure is same, only we are taking another surface. When you take another surface, you are not getting a magnetic field. So for the same point, same rule gives two values. So that creates a problem. So that's why this Ampere's law is not able to explain why it is like that. So what something is missing in that one. Now we have to search for what is that and why this problem came here. So if you think about this problem, see here we have a capacitor like this. So when you're charging the capacitor, a current is passing through this capacitor. That's correct only, because here the current is going, here also it is going. But inside the capacitor, electrons are not moving. So up to now, we explained all these things by thinking that the current is due to the flow of charge particle or some carriers it is charged. Here inside this capacitor, there is electric field. But we never consider that due to the electric field, some current will be there. We just takes the current is due to the flow of electrons. So now the thing is, here inside this one, inside the capacitor, without the flow of electrons, there is a current. That is not considered here. That made the mistake. So inside the capacitor, so we taken that here there is no current here, no current is crossing like that. There is no electrons passing there, or there is no charged particles passing there. But there is a change in the flux. This change in the electric flux, or there is a field. That field is making a current to pass there. So there is a current due to the field, electric field. That is called as a displacement current. I think the very basic idea of what is displacement current is clear for you. That is, inside the capacitor, the electrons are not moving, or any charged particle is not moving. Only because of the electric field or the electric flux, we have a current. That current is called as the displacement current. So we have a displacement current here inside. So now you'll see what is that displacement current. Okay. So we written too much here, so I will just erase a little bit. Okay. Now see here, we will calculate what is that, how much current will be there. For that one, first this electric flux, I told you it's due to the flux. So we'll take the flux. Electric flux is how much? Electric flux is electric field into modulus of electric field into area. So you know it's a capacitor. Inside the capacitor, the electric field is given by 1 by epsilon naught Q by A. So this is the electric field inside the capacitor. Into one more A is coming. So this A will come. So this will cancel. Then it will be Q by epsilon naught. So inside this capacitor, we have a flux which is given as Q by epsilon naught. Okay. Now, we know the d phi E by dt. How much it will be? It will be d by dt of Q by epsilon naught. Okay, this epsilon naught we can take outside. Then it will be dq by dt. What is special about dq by dt? That is current. So we can write d phi E by dt is equal to this 1 by epsilon naught into 1 current here. So this epsilon naught also we can take this side. So what you will get? I is equal to epsilon naught into d phi E by dt. So we got something like this. So what is this one? Inside the capacitor, there is a current, and that current is given by I is equal to epsilon naught d phi by dt. So displacement current means inside the capacitor, there is a current due to the change in electric flux that is given by this one. So this is called as displacement current. Okay, so that's about our displacement current. Now one more thing is there. Inside this capacitor, we already told there is a displacement current. So the total current in your textbook one equation is there. You should not have confusion in that one. So that also will be clear. Okay. So see here, the capacitor when you take like this, here we have IC, the conduction current. Inside this one, we have displacement current. Again, outside, we have conduction current. So our equation is in such a way that the total current I is equal to conduction current plus displacement current. I is equal to IC plus ID. So you generally people have a confusion how this total comes. But the situation is like this. Outside, when we have conduction current, there is no displacement current. When inside you goes, we have displacement current, no conduction current. So technically, we will write I is equal to IC plus ID, but the reality is outside I is equal to IC and inside I is equal to ID. So when this one is there, the other one will be 0. Just equation we will write like this. Okay, that's all. Now what we had to do is, why all these things are happened? Because we had used the Ampere's circuital law. So now what we are doing is, in the Ampere's circuital law, we will substitute this one, that is previously closed integral B dot dl is equal to mu naught I. That much was our Ampere's circuital law. Now the one extra term we will add. So that is called as Ampere-Maxwell law. So what Maxwell done is, all this calculation he done a small correction to the Ampere circuital law. It's not a correction, he added one term extra to that one. So this now what happens is, why we are studying this one with the electromagnetic this EM waves means, this is very important in the case of EM wave, because this correction he done, Maxwell, along with this one, Maxwell used other 3 laws also. These laws was not invented by Maxwell actually. Whatever law was already there, he understood its importance in the case of electromagnetic waves. He done so many experiments in the electromagnetic waves. So he understood these are the equations which is responsible for these electromagnetic waves. So only in this one he done some correction. Remaining he used as such. So I will show you that equations. It is there in your textbook also. This is called as Maxwell's equations in vacuum. So first one is E dot dA is equal to, this is our Gauss law in electricity. We already studied that one. The Gauss law is flux is equal to Q by epsilon naught. So this is one. And the second one is same Gauss law in magnetism. That also we studied. Okay. And after that we have the Faraday's law. And this one present. This all the 4 laws, if you check, you see one is Gauss law in electricity, one Gauss law in magnetism, another one is Faraday's law, another one is Ampere-Maxwell law. So these 4 laws was actually only this one he done little bit correction. This one was already existing. But he understood that all these law together, it is very much helpful in the electromagnetic waves. So all these laws together, it is called as Maxwell's equations. Okay. So these Maxwell's equations are actually considered as something which changed the world because of this electromagnetic waves, these communication systems. All these communications are because of this electromagnetic waves and its higher development, everything. So this is one thing which changed the world. So these equations, Maxwell's equations, are that much important. Okay, so that's about displacement current and our Maxwell's equation. Now we will move to the electromagnetic waves. So this is also very simple only. We will study about the source of electromagnetic waves actually. So what makes the electromagnetic waves? When we study each electromagnetic wave, I will tell you what is the source of each of that each type of electromagnetic wave. Here just the first concept was this electrons which is accelerated will produce electromagnetic waves. So once more, if you go from the basics, you know, if you have a charge, so if a charge is kept at a place, it will have an electric field around that one. A charge will produce electric field. And if you make a charge to move, a moving charge can produce, other than this electric field, it will produce magnetic field also. So that way, if you study, it will be clear. That is, if a charge is stationary, it will produce electric field. If the charge starts to move, a moving charge will produce magnetic field also. Moving charge only will produce magnetic field. Now, the same moving charge, if it is accelerated, an accelerated charge will produce electromagnetic waves. Once more, a stationary charge will produce electric field, a moving charge will produce magnetic field, and an accelerated charge will produce electromagnetic wave. Okay, so this accelerated charge doesn't mean that it's accelerating and going somewhere. The accelerated charge can be a oscillating charge. When it is from the center, it is accelerating towards side. So that can produce electromagnetic waves. And a charge which is moving in the circular path. So always circular motion is an accelerated motion. So circular path movement also can produce. So the source of electromagnetic wave, each and every type of electromagnetic wave from where it is produced, how it is produced, will study. But in general, the waves which we are using for communication, radio waves and such waves, microwaves and all, this produced due to the mainly radio wave. Okay, radio waves are produced due to the acceleration of electrons. When the electrons are accelerated, it produces the our electromagnetic waves. Now the next is about the nature of the electromagnetic waves, how these electromagnetic waves are transmitted, that one. So see here, this picture is very important. So how to draw this one, because many times this to draw this one only it came as a 2-mark question and all. So you think about a wave which is moving along z-axis. So when the wave is moving along z-axis, that is the direction of propagation is along z-axis. So its electric field will be in one direction and the magnetic field will be in one direction. So this electric field and magnetic field will be always in mutually perpendicular direction. So if electric field is along x-axis, the magnetic field will be along y-axis. Okay, then it is direction of propagation is along the third direction, that is z direction. So how you can draw it? So this is the z-axis and this is our y-axis. This is x-axis. So let the electric field oscillate along x-axis. So it is oscillating like this along x-axis. So I am drawing it like this. So why I am drawing this line means then you will get a 3-dimensional view of that one. So it is along the x-axis. Now the magnetic field is along the y-axis. You see here, the electric field and magnetic field in the electromagnetic wave, they are in phase. So when the electric field is 0, magnetic field is 0. When electric field goes to the maximum, magnetic field becomes maximum, like that. So this will be along this axis. It will be like this. Okay, so this will be perpendicular like this. So I think it's clear. The electric field is like this and the magnetic field, that is electric field is oscillating like this, magnetic field is oscillating like this, and the propagation is in along this direction. So that's how this electromagnetic waves moves. Now the equation for that one, the electric field is along x-axis. So I can write Ex is equal to E0 sine kz minus omega t. Okay. So here you see here, this electric field is along x-axis. This E0 is the maximum value of this one. Sine kz, what is k? I will tell you. And this z comes here. Kz comes means what is coming here in that direction. That is the direction of propagation. If an equation is given like this, in which direction it moves means, see here z comes, so it will be along z axis. Okay. So such questions can come. The equation will be given. From the equation, they can ask you in which direction this wave is moving. Okay. Now this E0 is here. Now what happens is the magnetic field will be with the same equation. So it will be By. It is along B0 sine k z minus omega t. So here also it is moving along z axis and everything is same. Okay. Now if this equation is obtained, how to write the magnetic field? That is very simple. Okay. This E0 divided by B0 is speed of light, c. If it is in vacuum, it is c. If it is in some other medium, it will be speed in that medium. So directly you will get this B0 will be E0 by c. That's all. So from that one, you can write this equation. Okay. Now here we written k. What is this k? That k is given by 2 pi by lambda. K is equal to 2 pi by lambda. So from this one, you can find the wavelength. See here. Here, if the k is there. If you put the value of k, you can find the wavelength. But when you do the numerical problem, you have a problem here. Here, this omega is the frequency. So if you take the frequency from the frequency, if you calculate the speed of wave, you will get a particular speed. And when you start with, you do it with k, you will get another value also. So which is right, or why you are getting two value, like that a confusion comes. Because many times children ask the same thing. If you put the value of k, k is equal to 2 pi by lambda, if you will get one value there for wavelength. And if you put this one, this omega is there, that is 2 pi by nu, then if you take the problem comes because when you write the equation of the wave, we consider that this wave is always moving in vacuum. Sometimes it may not be vacuum. If it is not vacuum, we cannot use that frequency into wavelength is c. If it is in vacuum only, it will be c. Otherwise, it will be in another medium, in the speed may not be c. So that's why it goes wrong. Okay. So the wavelength better to take from k only. From k, k is equal to 2 pi by lambda. That k, whatever equation you are getting, you make it to this format, and k is equal to 2 pi by lambda. From there, you take the wavelength. Because here, if you take wavelength, that issue comes. Okay. But if it is in vacuum, it will work. So you can get like that. So the questions which can come from this one is to draw this one. Another one is one electric field, one equation will be given. From that equation, you have to find what is the wavelength, what is the frequency, and in which direction it is going. And the electric field equation is given. You have to write the magnetic field equation. Like that, some questions can come. So displacement current one is there, and like this one topic is there from this electromagnetic waves. And we will try such questions. Okay. Now we will study about the electromagnetic spectrum. So this is the electromagnetic spectrum. We have to study this one in detail. Okay. What is happening in this each case. So I see here, this is that actually your textbook diagram, this one. So here we have frequency. So here 10 to the power 23 is the highest frequency. And here we have 10 as the, so the frequency nu is increasing this way. And this side we have the wavelength. The lambda is this way. Okay, so the frequency goes up here and comes here, and one by one we should know. So this is in vacuum. So actually, whether you have to by heart all this frequency means, if you can, it's good. Not to by heart entire thing, but the range, because it is not a exact value. For example, you have here gamma rays, and here you have X-rays. See here, they marked the gamma rays from here to here, and the X-ray is starting from here to here. So this much area, it can be called as both gamma ray or X-ray. Here also you see here, this X-ray comes up to here, and ultraviolet. That is something like a low frequency gamma ray or a high frequency X-ray. It's already same. It's just a wave. So the classification is not sharp actually. Just like something is there, if you take apple, a big apple or a small apple, if the small apple, if you take the biggest among the small apple, will be same as the smallest among the big apple. So there is no sharp exact boundary there. Up to this value, it is X-ray, and after that, it is gamma ray. Like that, it's almost, it will overlap. So almost the range you should know. This much range from the here to here, it will come like that. Only that was something which we take almost exact is for the visible light. That also visible means it is visible for a particular person. For every people, it may not be same. So we'll start from this visible light. Okay. So you see here, I will draw on the top so that instead of drawing like this, the same thing here. So we have the visible light here. When you take the visible light, this much area is visible. Okay, in the spectrum, where I'm talking about full spectrum like this. So we have the visible light here. So the visible light is having a particular wavelength. How much it is? Visible light is from here, you can see 400 nanometer to 700 nanometer is visible light. Okay. So if I take here, so visible light, this 400 nanometer, the wavelength is very less. That will be violet. Here violet, and here it is red. This side violet, and this side violet, and that side red. So that is visible light. So all the other colors are coming. So you can see that the center area is coming 550, 540, and all is yellow, green, and also we will be more sensitive toward that one. Okay, it's coming in the center. Now see here, If you go towards this side, so this frequency is this side, okay. High frequency is going this side, wavelength is going towards that side. So the near to the red, which one will come? Infrared will come here. So why it is infrared? It is infrared because the frequency is less than red. That's why it is infrared, inferior to red. So infrared is coming here. And after this side of the infrared, what is coming? Microwave is coming. And after microwave, we have radio waves. So this radio wave, so much calculation is there. So see here, this much calculation is there in the radio waves. Different types is there, that one by one we'll discuss. So this is how you have to do. So you have the visible light, and we have red at one side, and near to the red we have this, easy to remember, this infrared. Then again next is microwave, and we have radio wave. And the radio wave is having the longest wavelength. So the frequency will be very less. And you know the frequency and the energy is related. So this side the energy will be less. When it goes to this side, the energy will be more, because here the frequency is more. Okay, so we have the frequency here, less frequency, more wavelength. So you can see here the radio wave is having a wavelength in meters or in kilometers also. That much long waves are there. But the frequency is less. And when you are going to the higher level, what happens? The frequency is coming very high. That is 10 to the power 22, 10 to the power 21, and all is coming very high frequency. So the wavelength will be very small, 10 to the power minus 13, 10 to the power minus 12, that range it will be. It's very short waves. So whenever the waves becomes short and the frequency increases, its energy will be more. So here infrared is there, microwave is there, and here radio wave is there. That's why radio waves are actually having less energy. So we are using all radio wave for communication and all. And when you study the diffraction and all, you will understand these waves will bend actually. When you go to this side, these waves will go straight. These waves will have the tendency to bend. So that's why inside a room also you are able to listen to the radio, because this is radio wave can bend and microwave can bend. Infrared won't bend like that. This light also will not bend. When it goes this side, the bending will be very less. That is X-ray and gamma ray and all will not bend like that. So here red, and that side we take. Now here violet. Now here we have ultraviolet. Something is more than violet. The frequency is more than violet. That is ultraviolet, which is coming here. And again more than that one, we have the X-ray here. We have X-ray here. And again more than X-ray, we have the gamma ray here. So this is the electromagnetic spectrum. So the frequency and this range also, I told you, exact value is not there, almost range, because many times about X-ray it came. This particular value of frequency or wavelength is given, and this one comes under which category, like that. So at least you should know what are the things coming under this waves. So electromagnetic waves. So starting from the frequency, low frequency, radio waves are coming. In radio wave itself, we have long radio wave, AM wave, television, and the short wave. All these things are radio waves only. And after that, we have microwave. So microwave is having higher frequency than radio waves. And after that, we have infrared. All these things have energy less than our visible light. Then visible light comes, in that one all the colors will come. So this side, infrared side, the red is coming, and the other side violet is coming. After above the violet, we have ultraviolet, then we have X-ray, and then we have gamma ray. So these gamma rays will have the highest energy. Okay, now these things we have to study in detail, how these waves are produced and what are the uses of this one and how we can detect that. Things we have to study in detail. So first we will go for this table. This is also there in your textbook. So first we will think about radio wave. So radio wave means they will have the wavelength more than 0.1 meter, that is 10 centimeter or more. Radio waves are having 10 centimeter or more wavelength. And see here, starting from 10 centimeter up to meter, kilometer, everything is coming under radio wave. And you see here, the production, rapid acceleration and deceleration of electrons in aerials. Aerial means the antennas. Okay, so if electrons are accelerating, that produces the radio waves. So it is using electronic circuits it is made. So the radio waves are that one, okay. And uses and all we will discuss like this. And how it can be detected. So that is radio waves are produced by an antenna. How we can receive that one? For that one also we will use the receiver's aerial or antenna only. Now the next one is microwave. So the microwave you see here, it is 0.1 meter to 1 millimeter. We are going down. That is 1 millimeter to 10 centimeter wavelength. That is coming under microwave. And the microwaves are produced by this klystron valve or the magnetron valve. So don't forget to study this one, because they can ask opposite. Which wave is produced by klystron valve and which one is produced by magnetron, something like that, and details of that one. So this one you should remember. This waves are produced by klystron valve and the magnetron valve is microwave. And this microwave detection is using the point contact diode. It's just like how you are using the solar panel and all. We have point contact diode where we can use to detect the microwave, okay. And use and all we will discuss later. And after that we have the infrared. So the infrared is 1 millimeter to 700 nanometer. What is special about 700 nanometer? That is near to the wavelength of red color. So red is 700 nanometer. So from there to 1 millimeter, that is infrared. So that is produced by vibration of atoms and molecules. That is very important. Infrared radiation is produced by the atoms and molecules. When it is vibrating, it will make infrared. Actually, infrared is same as heat radiation. Say hot objects produce infrared. So when the object is hot, the particles are having more energy, so the vibration is there. So that you better study in 11th standard. If this pen is at lower temperature or when it is hot, what is the difference between that one? When an object is hot or cold? When it is hot, no mass or nothing is added to this one. Only thing is the particles of this one is vibrating. It's getting more energy. That's why it is vibrating. That's why it's hot. So that vibration makes the infrared. So if what is the frequency of the infrared coming from this one, if you detect that one, you can find the temperature of this one. That's how when you have fever, especially in the COVID time, you have seen one small thing is used near to your forehead to check the temperature, whether you have fever or not. So that is working based on this one, because according to your temperature, some infrared will come from there. So that if you check that one, what is the frequency of that one coming out, we can take the temperature without even contact. So this infrared radiation is heat radiation that you will study later again. So this is received by thermopiles, bolometer, and infrared photographic film and all. So these are all old one. Okay, now we are using no direct sensors itself. Okay, to do that. Okay, then next is light. So light is from 700 nanometer to 400 nanometer. How light is produced? That's also an important question only. How light is produced? We have a bulb or we have a lamp. So inside that one, what is happening? How the light is produced? So for example, you are firing something, from there light is coming. So actually what happens, when you fire that one, we are supplying some energy. Due to some chemical reaction also energy happens. So these electrons are going to a higher energy level. And from higher energy level, when into the energy, the electrons are coming down, the extra energy is coming out. So due to the transition of electrons from higher energy level to lower energy level, the energy is released as photons or light, because light can be considered as photon. Later you will study that one. So the light is emitted because of the electrons in atoms emit light when they move from one energy level to the lower energy level. So the electrons are coming from higher energy level to lower energy level. They will radiate light. That's how the light is produced. And what are the things to detect that one? The human eye, that is, you can see it. And photocells. Okay, photocells are something which detects the brightness and all. Okay, then photographic film, that is not a normal film it can use. Now we have the ultraviolet. So ultraviolet means, you see this 400 is the edge of this one, less than 400 to 1 nanometer, that is coming under UV. So is ultraviolet radiation also, it is also produced by the transition of electrons only, but where the transition takes place is different. This light is from the lower energy side, and this ultraviolet will be little bit inside. So inside means there the energy difference will be more. So for inner shell electrons transition makes ultraviolet. So it is also the photographic plate and the photocells, everything can be used for detection of that one. Now, after that we have X-ray. X-ray also is produced. See here, this wavelength you have to by heart. Okay, this 1 nanometer to 10 to the power minus 3 nanometer. If you study this. This is actually 10 to the power minus 3 nanometer can be taken as micrometer. Okay, so this from micrometer to nanometer, if you do, it will be easy. So this X-ray is produced by the inner shell electrons. Okay, actually we have something called as X-ray tubes. So there the same thing only, just like the our light only, but it is the inner shell. Okay, and see outer shells electrons that will produce light, and little bit inner shell it will make ultraviolet, and again more inner shell. For all elements it is not same. Okay, so it will make X-ray here, and X-ray also photographic film, everything is same only. And gamma rays is the highest energy thing. It is 10 to the power minus 3 nanometer, and this gamma rays, it's very, very important. We cannot produce using this our electronic circuits or something. This gamma rays is having very high energy, so that is produced only due to our nuclear reactions. So we cannot produce it in another way. So if you need gamma rays, we should have a sample which produces gamma rays. We have to keep it. We cannot do it our own, but we can induce that one. That's a different matter. So gamma rays are produced by the nuclear decay of that one. Okay, so and the detection is same. And if you take the energy of the highest penetration power and all will be for this gamma rays. Gamma ray can penetrate up to iron or steel, up to even 30 centimeter steel, it can penetrate high energy gamma rays. It's having very high penetration power. So this is about its general production and the wavelength and all. Now the use and all we will discuss. Okay, so one by one we will discuss. So the first one is radio waves. So radio waves, what are the uses of radio waves? Very simple. Radio waves are used for communication, radio and television communication system. Here also we have one more classification. Once you have to read that one also, because the frequency or the wavelengths up to where we are using, because we have short wave, we have medium wave, and we have FM. Generally from, you might have seen when you are tuning the FM radio, it is coming from where to where. Generally 88 megahertz to 108 megahertz is used for FM transmission. So different transmission, different range is used. Up to 54 megahertz generally used for TV, and above that one it is used for satellite communication. Another one is used, and we are using for short wave. So that numbers, if you know, that is good. Okay, it is there in your book, each one for different types of radio signal what it is used. And one more thing for cellular phone. What is cellular phone? It's mobile phone only. So our mobile phone, we are using radio waves only. Why this is called as cellular phones? Out of topic still. You have so many antennas in different area. So this each area is divided into a cell like this. Okay, so your entire district is divided into different cell, and in the center of each cell you will have an antenna. So that's why that cellular network is there. That's why it's called a cellular phone, or just our normal mobile phone. Okay, so this mobile phones uses radio waves. That is very, very important. So you should know the radiation of mobile phone is having very, very less energy. Okay, so that's why. Otherwise, if radiation is that much danger, so many brands of mobile phones are working, so much communication is going on, that will harm us like that thing. But it's not happening like that, because the radio waves, the mobile phone is using radio waves, it's having less energy than light. Light energy, comparing with light, the energy of radio waves is less. Okay, so that's about cellular phones. Now we have microwave. So this use of microwave, in that one very important thing is about the radar, because the expansion of radar, when you take it is radio detection and ranging. So this radar is used for navigation, actually, for aircraft navigation, for ship navigation and all. So here this radar, this R says radio, but I told you that overlapping is there. So if now presently what we are using for radar is microwave. Okay, so don't confuse in that one. The expansion when it is coming, it is radio detection and ranging for finding the position of the aircraft or finding the position of the ship, or for any navigation purpose we are using radar. So even though we are using the word radio here, the wave used for radar is microwave. Okay, so you should not have confusion in that one. So these microwaves are used in radars. Okay, and next one is another use of this microwave is the speed gun. What is speed gun means? During cricket match, even each ball, you can see on the screen, they are telling the speed of the ball, this much kilometer per hour or this much mile per hour, that speed of the ball is there. When something is moving, its speed we are using, we are finding out using speed gun. For that one, we are using microwave. The ball speed during the play, what speed, especially it is, you can see in cricket. And one more, generally now another one you can see, the speed cameras. Which is used in the traffic by the traffic police or the motor vehicle department. They will fix that something over their vehicle or on the roadside, so that they can see the vehicle and they can take the speed of that one. A moving vehicles or a moving car speed we can find out. So that there we are using these microwaves for speed gun. Speed gun means something which measures the speed of a moving object. For vehicle speed we can find out, or a moving ball speed we can find out. All those things are done using microwave. Actually, there is something called as Doppler effect, where we are making use of that one. So the microwaves are used in speed gun. And the other one, microwave, very common, where when the word microwave comes itself, what is coming to our mind is microwave oven. Okay, so for cooking we are using microwave oven. So how it works? So in that microwave oven, you might have seen something like a light is there, so which produces a microwave. So inside that one, you are keeping some materials for cooking. So that contains water. That working is very important. So this one contains water molecules. So when microwave is passing through that food material, you will see that it is, we are not using for frying and all. We always, that will have any such food materials, it will have some water content. So when the microwave is passing through that one, we already studied the resonance. So what happens? The water molecules will start to vibrate. Actually, vibration, or you can take it as rotation. So this vibration or rotation, when it is matching with the microwave, what will happen? Its amplitude will be maximum. So there are some chemical bonds inside this food material. So that chemical bonds will break, so that it will heat up. So that's why the microwave, there are some special vessels you can keep. We are not using metal and all, and we are not directly heating it. So when the wave is passing through that one, the water molecules, they will have a resonance with that one. So because of that water molecules, that itself getting heated up there. That's how it works. So there also we are using microwave. Okay, so it's something like the resonance phenomena only. So when the microwave is passing through that one, so whatever is there, so that particles will start to vibrate, especially the water. So that creates energy from inside. That cooking happens like that. It's not by heating. So you may have noticed that one. Sometimes the plate or whatever you are keeping, that may not get heated up. And even with the plastic covers, if you put in plastic cover and tie and like that also, it works. Okay, better not to do, but it works. Okay, so that's how this microwave oven works. Okay, that's based on microwave. Now the next is infrared. So in this infrared is also called as heat waves. Already we discussed the infrared is heat waves. So a hot object produces infrared. Okay, and in junior class you studied the greenhouse effect. Infrared is responsible for greenhouse effect. Infrared is responsible means it is not that infrared is coming and making this greenhouse effect. Even when the light is coming, for example, you have a car, a closed car. Inside the car, if you keep in the sunlight, it will be very hot. So what happens is the light is entering inside, not infrared. Light is entering inside, and all the surface of the car, just like your seat and all black objects or whatever is there, all these things will absorb this light. So this through the glass it is coming inside. But when it is absorbed, this will re-emit. When this your car seat or other objects, when it is re-emitting, it is not re-emitting as a light. The car seat absorbs the light. From there, light will not come back. What is coming back is infrared. This infrared cannot pass through the glass. So this gets trapped inside. So that a closed car will be very hot after half an hour if you give it sunlight. Not only for the closed car, your earth is like this and we have the atmosphere like this. This acts like a closed car itself. So the light is coming inside. From here, when it is reflecting, it will be infrared. That gets trapped inside so that the global warming is happening. So this infrared is creating our greenhouse effect. But one important thing is there, the light, along with the light, we have the heat also. Sun's heat energy is coming. From sun to earth, this heat energy is coming as infrared only, because there is no medium between sun and earth. So that is also very, very important. The heat energy from sun is coming to earth as infrared, but you have to remember that our solar panel is not working based on infrared. Solar panel absorbs light, visible light and doing. It's not based on, so there is no heat required for solar panel to work. If light is there, that is sufficient. It doesn't mean that always should be hot or something, just light is sufficient. But infrared actually carries the heat from sun to earth. And one more, any hot object, it will produce this infrared. Okay. I told you to measure the heat and all. And I see here the Earth satellites. The satellites are taking the picture of Earth and it is taking the infrared. You might have seen when the climate it is given in TV, they will show a yellowish graph. So these Earth satellites are using that one. Okay. And again, military purpose, same thing only. The temperature, if you, some people are hiding on a, inside a forest. If you take an infrared photography, wherever people are there the temperature will be different. So in infrared photography, whether the people are hiding, that we can find out. Okay. And this growth of crops also, in large area when crops are there, if you take the infrared photography from the temperature, we can find out whether it is what level it is written. Okay. And one more very, very important and very common use is this TV remotes. The TV remote, if you take the remote, the top of that one, you can see something like a LED light. But when you press, mostly it will not, you will not see any light, because the light, it is what is coming out of that one is infrared. For most of the remote controls, we are using infrared. So one side infrared LED will be there, another side infrared sensor will be there. So the communication is going as infrared, not as light. Now another one is physiotherapy. Physiotherapy, this is not there in your textbook. So, but you should know that one. Okay. So in physiotherapy, we are using infrared radiation to loosen the muscle and muscle problems and all. We are using physiotherapy. It is, we are using this infrared, direct infrared radiation. So lights we can use. Not only this infrared light, even if you are taking some cloth dipped in hot water and if you are keeping, that also gives the heat. Infrared only. Okay. Then the thermal imaging cameras. You can take the thermal photos, the temperature photos, just we discussed. And again, night vision camera also in CCTV and all, night vision is there. So night vision cameras works with. So all these things you should know infrared wherever it is used. Now we have visible light use and all, no need of telling, just the wavelength, frequency, range only you should know. And UV rays. See here, UV rays, first junior class you studied. This UV rays will produce cancer, it will create cancer. So this to protect us, we have the ozone layer. So ozone layer protects us from cancer or such things. So the ray which is blocked by the ozone layer, that is this one. Okay. And the melanin, that is our skin color, will change because of this one. And those who don't have, or those who have less melanin, they will take sun bath, so that when light falls on their skin, more the more tanning will happen. And one more main thing about this ultraviolet is, it is absorbed by ordinary glass. So question can come based on that one. You cannot get sunburn through a window glass. Why? Because sunburn is happening because of UV or ultraviolet. So through a glass, it will not happen because the UV is absorbed by ordinary glass. And now one more thing is there, when you are doing the welding time, you will see very bright light. So in that one also UV is there. So they will use a special glass or a mask type thing they will use. Okay, so that they are protecting their eye from this one only. Okay, that ultraviolet. Then one more use of ultraviolet is this LASIK. What is LASIK? LASIK is a treatment, eye treatment. Okay, for this LASIK treatment is for that one also we will use this UV laser only. So that also you should know. And again, it is used for in water bottles. You will be there RO water in that one UV treated like that. So to kill germs in water purifiers, we are using UV. So all these things are the uses of this one. I told you, you cannot skip one also. Each and every use you should know. Next is X-ray. You know X-rays. It's a very simple thing. And where it is used, X-ray is used as a diagnostic. In medicine, we are using this X-ray to check whether any bone fracture is there. And one more, it is used for treatment of cancer. Actually, cancer treatment, we will use gamma rays. I told you, the X-ray and gamma ray, that there is no sharp boundary. So X-rays use and in gamma rays use, both places this cancer treatment is written, but mostly we'll write in gamma rays, okay, because that is having higher energy. Here we can write it as for diagnosis it's used, and it is again used for crystal diffraction or to study the crystal structure. So you might have heard in chemistry that packing, BCC and all. So what is the structure of the crystal? To study that one, we have a method called as crystal diffraction. For that one, we will use X-ray. So X-ray diffraction we will do, and based on that one, we can study the structure of the crystal. So there also we will use X-ray. So now the last one, we have the gamma rays. So we already discussed gamma rays are produced by nuclear reactions, and it is having very high energy, and it is emitted by the radioactive nuclei, and they are used in medicine to destroy the cancer cell. That is this is what we call as the radiation treatment. So we have particular sample which produces radiation. That radiation is used to kill the cancer cell. This is for radiation treatment. For cancer, we are using this gamma rays. So that's the use of gamma rays. So I told you already, once more I am telling, each and every use you have to study. Okay. So there is no much numericals or problems from this one. Only that equation is there, that previously we done E is equal to, from that equation to find the wavelength frequency, such questions only can come. Remaining always this use, based on the use only it will come. So this one we finished. So now we will, if any possible numerical is there, we will do this one, and next session we will discuss about our ray optics also. Thank you. Now the time is over. We'll stop now.